we have seen symmetric encryption scheme, but the world is using, I mean, the internet has been successful probably because we have an additional thing that is called asymmetric cryptography. If we had not this, we would not be using, or will you be using the internet for perhaps a number of things, but certainly not for e-banking or for authentication here. Because symmetric cryptography requires that the secret key is shared between the two ends. So how do we share a key between the two? How do I have a secret key between me and my bank? If we don't have asymmetric cryptography, then I need to go to the bank physically one day and share the key in a mechanism. For example, there are mechanisms for that. I could scan a QR code that the bank gives to me by physically going to the bank. And only after doing this, I have the secret key, which I can use for doing e-banking. But probably none of us did this, right? We just subscribed to the bank, and one day you receive mechanism. Perhaps a password is sent by the post office to you, and that's all you need to do that kind of thing. This is possible because there exists what is called asymmetric cryptography, or also called public key cryptography, that essentially solves this problem of not having to share, to first agree on secret keys here. It can be used for encryption and for authentication, just like we've seen symmetric key can be used with AES for providing these two functions. So it can provide the same thing here, but with an asymmetry between the keys. How does it work for encryption? The mechanism is the same here, assuming I have a text P that I want to send and I want to keep secret. Then with such a scheme here, there are two keys, a public key and a private key here. And the encryption key, here the public key is used as encryption key, is public here. For example, posted on a website is the key of the bank. It's not the key that the bank gives to me, but it's the key that my bank has. Still need to make sure I have the correct key, but it's only one key per bank, not one key per customer of the bank here. So it's public, but the decryption key is secret here. It's called also private here. So the text is encrypted using the public key here that provides a ciphertext. Anybody can do this, including the bad guy, could encrypt here. But only who, or at least if the system works well, only whoever knows this private key is able to decrypt. So for anybody except the guy who has the private key, in the case of the bank computer system, only the bank can decrypt the system that I'm sending. So for the rest of the world, once it is encrypted, it is a random sequence of hexadecimal digits. And the paradox, what's the miracle? How can it work? Is that anybody can encrypt here, but decrypting is only possible if you know the private key. So it means we have what is called a one-way function. That we can do the computation easily in one way, but inverting the computation is impossible or practically impossible unless you know the secret key here. Here is how it works. At least one of the most widespread systems called RSA from the initials of the three authors, which was done in 1977. And this is really what made secure internet possible. It's exactly this system here. Here is how it works. It uses also number theory. We have an exponent, for example, this one here, to the power 16 plus 1. And the public key is the product of two large prime numbers. You take two large prime numbers, you multiply them, and that's the public key. And the private key is the factorization of this. Now, it looks stupid. Let's illustrate one. If I give you the product of two prime numbers, like 33, and I ask you to factor it, you will say, well, this is 11 times 3. So this is the public key. The private key is not so private because everybody can factor 33 into 11 times 3. But if I give you this number, and I ask you what are the two, and I say to you, it is a product of two prime numbers, and find them, it is known to be a very hard problem if the number is very large. People have been working very hard on this problem. There is, of course, the brute force approach with Eratosthenes system, You can, but the only simple approach is to try all the prime numbers until you square root of this, until you find one that divides. But this is time consuming. So if you have very large numbers, today the numbers that we use with RSA should be at least 256 bits long. So the size of an IPv6 address square. And it is believed that if I give you such a number, now there is a lot of science about RSA. There are some numbers that are easy to factor, so there are ways of generating such prime numbers. Typically, they are powers of 2 plus or minus 1. And if you have such numbers, there is no good way of getting of factoring it other than using all the computers of the world during hundreds of thousands of years in order to factor one such number here. Except if you have a quantum computer. We'll talk about it a bit later. If you don't have a quantum computer, it's believed to be impossible to factor this into two prime numbers. So given this, the private key is in fact the factorization of the public key. And then the encryption scheme uses what is called the Chinese remainder theorem, which works as follows. To encrypt a message, or first we chop the message a bit like with AES into blocks that correspond to, that can be interpreted as integers modulo k, modulo this number here. Then a block, which is interpreted as a number, is computed to the power e. So e is this here. So I compute this to this power, and that gives me the ciphertext. You can say if the number is very large, if k is very large, computing to the power e is something very complicated, but this is not true. Computed something to the power of a large number is something simple because it's just multiplications. In particular, if this is a power of 2, because if I multiply a by a, I obtain a to the power of 2. If I do it again, I obtain a to the power of 4. If I do it again, I obtain a to the power 8, etc. In 4 operations, I have obtained a to the power 16. And so it's in 16 operations here, by multiplying the number 16 times by itself and multiplying again by itself. So in 17 multiplications, I have obtained this here. So even if this is a large number, this is not, you don't need to do a large number of multiplications, but if this is chosen as a power of 2 plus or minus a small number, which is typically done with RSA. So that's easy to do. The decryption, or relatively easy to do, the decryption uses something similar, but it uses the private key. So the private key is P and Q. So in fact, we need the product P minus 1, Q minus 1, or to simplify, the least common multiple of this, but that's a small detail. And the inverse of this modulo the private key. Now, what is the inverse modulo? Where when we do modulo arithmetic, so if I do computation modulo 33, for example, that means 34 is equal to 1. And the inverse of a number modulo something means another number such that the product of the two are equal to 1. In standard algebra, the inverse of 2 is 0.5 because 2 times 0.5 gives 1. So if I'm doing modulo 33 here, and if I have a number, I need to find number such that the product of those two gives 1 modulo 33. So the product is equal to 34, for example, or 67 or whatever, all the multiples of 33 plus 1. And arithmetic theory says to us that if k is a prime number, if the number that if this number here is relatively prime with that one here, that it has an inverse, and it can also easily be computed within an algorithm called Bezout algorithm that some of you, I'm sure, have seen when they were young in high school. That's an algorithm that's used to compute the largest common divisor of two numbers. It can be used also to compute the modulo inverse. We don't really have to dive into the details, but it's just that all those applications have polynomial time complexity. They're not extremely fast like AES, but they're not astronomically complicated like factoring a number. So those are things that can be done by a computer in relatively short time. So once you have the inverse of f, you have the Chinese remainder theorem that says if I have a number m that I've taken it to the power e, then if I take it again to the power f, modulo k, which is the same as taking it to the power EF, it will give the same as M, because EF modulo this is 1 here. So it'll be too short to be able to understand, but that's the magic that's behind it, which means that if I know the secret key, if I know the K here, if you give me C, I put it to the power F. Now, F is perhaps not as nice as this, so it can be done in a larger number of steps, but it can be done. And then I will recover the M here that I know, which is the decryption here. Let's do a toy example. Of course, we will never use a public key 33 because it's the private key is not so private, but that gives us an illustration of how it works. If I take 33 as the public key, then the private key is the factorization, 3 and 11. So P minus 1 is 2, Q minus 1 is 10. I said the private key is this, but to simplify the computation, we take the least common multiple of 2 and 10, which is 10. So 10 is the crucial number here. And I need to find the inverse. So if I use as exponent 7, I need to find the inverse of the exponent modulo 10. So 7 times 3 gives 21, which is 1 modulo 10. So the inverse of 7 modulo 10 is 3 here. And now if I have to encrypt a block, which is interpreted as a number modulo 33, a number between 0 and 32, therefore, I put it to the power 7 here. And then the theory says that if you receive an encrypted block, you put it to the power 3, then m to the power 7 to the power 3 is m to the power 21, which is m to the power 1, which is m. So I've done it here with a message. The message is bonjour. Each of the letters are translated into a number between, I said 0 and 32, in fact, between 1 and 32, for obvious reasons. If we put 0, the ciphertext is 0. So if you put a 0, you will know the clear text was 0. So we never use 0 here. So B is the second. So I give A, I encode A as 1, B as 2, etc. So that gives me this plain text for the input. I put everything to the power 7. So 2 to the power 7, that gives 128. I compute modulo 33, which means I ask MATLAB to compute it, or I divide 128 by 33, and I look at the remainder when I do an integer operation, and the answer is 29. I do this for all of this, I obtain this, which is a sequence of encrypted numbers between 1 and 32, which has nothing to do with the original text. But if I know that the magic exponent is 3 here, if I compute this to the power 3, 29 to the power 3 will give something, which modulo 33 will give exactly 0, will give exactly the 2. So I can recover the text here. And what I need to publish is only 33. And what is secret is the exponent 3 here to do the inverse computation. What is public is also the other parameters of the system. The exponent 7 also needs to be public here. So anybody can do the encryption by doing this step of computation, but only me, who owns the decomposition here, can compute 3 here and do the reverse. Of course, you should imagine that instead of 32, we have an astronomically large number, and computing this exponent here, which will also be astronomically large, is something that is believed to be hard here. This is how RSA works. It is secure. It is believed to be secure today. I said 256, I was wrong. It's not secure at 256 keys. Sorry. Today is believed to be secure when the key size is larger than or equal to 2,000 bits. If the keys are smaller, it's hard, but not impossible to decompose, to factor the key into its prime numbers here. So as long as the decomposition number, the factorization problem is not solved, then we are safe. And this is used practically everywhere today. Now, if there are quantum computers, so what is a quantum computer? Well, a computer is something that has bits that are encoded by transistor states, zeros and one. A quantum computer is something completely different, where it doesn't have bits. Instead, there's something that are called qubits. A qubit is not a bit. It is something that has a state, and the state is two complex numbers. So it's an analog state. It's an analog computer with a strange property coming from quantum physics that if I have n qubits, the state of the n qubit is not n times the state of every qubit, but is 2 to the power n, the number of states. So that because the state of the combination of two qubits is not the first qubit and the second qubit, but the combination itself can have a state, so that if I have a number of qubits, the possible number of states, the dimension of the set of states, increases exponentially with the number of qubits, which means that we're able to solve problems that have exponential complexity, at least in theory, because it's an analog computer, and the only thing you can do with a qubit is do a measurement that will return a 0 or a 1, even though the state is a huge, monstrous, complex number, continuous, analog, everything. At the end of the day, you do a measurement, you destroy the state, and you have only a 0 or a 1. And with noise and decoherence and lots of problems. So many people, particularly in physics department, believe that we will have in the future quantum computers. Not everyone, even in physics department, agrees on that. So we will see, you will see, perhaps I will not see because I will die before. You will see whether there will be quantum computers. But if there are quantum computers of decent size, today you can build a quantum computer with 53 or 56 qubits. Why such a strong number? Because they tried with 64, and then they found out that a few of the qubits don't work. It's analog systems, so when you build analog systems, right, there is noise, there are many things that can make the system fail. But it's believed that if we can make computers that have 10,000 qubits, the plans for that are supraconductor things at temperature that are -2, lower than -200 degrees, so extremely exotic and complicated things. But if they might exist, then we can break all the RSA keys. So therefore, people are doing other things like lattice cryptography that will replace what I could explain in 2 minutes, how RSA works, in something that I could not explain in 2 minutes. But there are other cryptography mechanisms that are so-called post-quantum that are at least not known today how we could break them, even if we had a quantum computer here. So this is illustrating, again, the same thing we had when we talked about symmetric cryptography. 20 years ago, symmetric cryptography was DES. Then DES was broken, and then we need AES. 20 years ago, asymmetric, and even today, asymmetric cryptography is RSA. One day, RSA is attacked if the key is small. If it's very large, then it is still safe today, but in the future, it might break here. So other systems are used, elliptic curves, lattice cryptography, which have the same security with much smaller keys. And in the case of lattice cryptography, is believed to be not broken by quantum computers, which means that the cryptographic system that a system uses may need to be changed when there is an advance on the front of cyber crypto analysis. If asymmetric cryptography would be easy to implement, then we would use it all the time because it's so convenient. If the PMU sends things to the PDC, then it can encrypt things with the public key of the PDC. So you have 10,000 PMUs. I just need to write into every PMU the public key of the PDC. That would be very easy. But as you can see, for example, if we use keys that are 2,000 bits long, it is computationally much more expensive than AES by 2-3 orders of magnitude here. So in practice, we don't want to use it too much. It's possible. We use it in some settings. For example, when we have multicast cryptography, that's the only thing that works. But what is most of the time used is hybrid encryption. Hybrid encryption relies on the fact that we will use symmetric cryptography, but we will use asymmetric cryptography to get temporary keys. Here is how it works. When you go to the bank, for example, you get from the bank you have the public key of the bank, and then you send you compute, you choose a random number, truly random number here that cannot be guessed. You didn't know this number before choosing it, and the bank doesn't know what this number is. Before you send it encrypted using asymmetric cryptography. So you encrypt it with the public key of the bank, you encrypt this session key here. Now, because the public key, the private key is known only by the bank, now the bank knows your private key here, knows the secret key, and any attacker that reads this cannot obtain the secret key L here. And now, when you, for the rest of the and that will take some time. It will take 2-3 seconds of establishing this secret key here. That's why when we go to the bank at the beginning, it takes some time to number crunch everything. And once this is computed here, the rest of the communication with the bank will use the secret key L that we have computed with AES, because that will be most lightweight, and that will be very lightweight and very easy. So L is called a session key, whereas the public and private key of the bank are permanent, or at least they don't change very, very often. This is called hybrid encryption because it uses both asymmetric and symmetric, and is motivated by the fact that asymmetric cryptography is too heavyweight to be used for every bit and byte that we send here. Little quiz. Closing the poll in a few seconds. And the majority says C, which is the correct answer. If I encrypt with the PMU's public key, then the PDC will not be able to decrypt because the PDC does not have my private key, so it's useless. If I encrypt with my private key, then anybody knows my public key is public, so anybody will be able to decrypt, which is not really the goal of encryption. That's not a good idea either. The PDC's public key works. I encrypt it. That's what we saw a few minutes ago. I encrypt it. Anybody can encrypt, but only the PDC will be able to decrypt here. If I use the PDC's private key, well, I cannot because it's private, and the PMU is not supposed to have the PDC's private key. So it's answer C. It's the only one that is possible here. Yet another question. Closing the poll in a few seconds. Closing. Majority says F, which is the correct answer. Should mark the solution, like I'm doing now. This is a hypothetical example where all end devices want to communicate with each other, which is not at all typical. You typically have a number of servers that everybody communicates with, and all the servers perhaps communicate with each other. But if we take this assumption as valid, we have n devices that communicate with each other. Then with symmetric cryptography, we need a pair, we need one secret key for every pair of devices. So there are n minus 1 over 2, so order of n square symmetric keys that must be deployed. That's the problem of symmetric encryption. With asymmetric cryptography, we need one public key per device and private key, so one key pair per device, and then everybody will use the public key of the destination with whom we communicate. So there will be only order n. That's one of the major advantages of having asymmetric cryptography. We have seen asymmetric cryptography being used for providing confidentiality. It can be provided also for authentication. And when it provides authentication, very similar to a tag, it will provide also what is called a signature. Signature means a non-repudiation. Once somebody has the signed document, whoever signed it cannot claim that they did not sign it. That's why we call it a signature. It provides also authentication like a tag, but it provides authentication and non-repudiation, so it's a signature. With asymmetric cryptography, it works very easily, at least with RSA, by simply exchanging the roles of the private key and the public key. If I have a message and I encrypt it, so a message that I say it happens to be just a block that has the size of the required by RSA, so the size of the public key K, if I compute the decryption function applied to the message M, so M to the power F here. Remember, F is the secret key, the private key that we need to keep secret for RSA, which is used for decryption. RSA will compute M to the power E on the sender side and decrypt it by computing M to the F. If we exchange the order, if I compute M to the F, then by algebra works the same way in finite fields as it works in ordinary numbers that we use every day in MATLAB, then M to the power E to the power F is the same as M to the power EF, which is the same as M to the power F to the power E, which means that if I compute M to the power F here, I send it over the internet, plus the message, so this is my signature, S. If I send S, and the recipient receives M and S, the recipient can, using the public key, that corresponds to me, can decrypt or can apply the encryption for compute S to the power E, and the computation of RSS that says that S to the power E is equal to M, because the functions of encryption and decryption, which normally work in one way, first you encrypt, then you decrypt, and then that gives identity, that gives the original message. In the specific case of RSA, it works also in the reverse order. If you first decrypt, then encrypt, then it gives also the original message, which gives a way of providing a signature, because now if somebody receives S, then anybody can verify, because the decryption, this key capital K is public, but the S can have been computed only by somebody who has the private key, K here. So when I receive MS and I do this test, I compute EK of S and I obtain exactly M here. Then as long as RSA is not broken, I can be sure that the S has been computed by a device that knows the private key K. So that's a signature, because it means this has been computed by somebody who has the private key. And when you have the private key, you sign somewhere a contract that says, I accept the fact that anybody who signs with this private key is considered like being signed by me here. Of course, it works as long as RSA works, so it needs the key to be large enough for factoring to be impossible here. So this is what is called the RSA digital signature. Now, there is still a problem that it allows you to sign only a message that has a given size that can be on which you can apply the modular arithmetic. What if I have an entire text to sign? If it's smaller, I can pad it. But if it's larger, what do I do? Then I need to do what is called reducing a long message into a short one. And this is done by what is called a hash function. I'm sure you've encountered already hash functions. When you program in Python, for example, and you have large tables with 10,000 entries that are long sequences of numbers, then you can use primitives called hash tables that will make them shorter. What is a hash? A hash is something that takes a long message and makes it shorter in a way that is hopefully completely random, but completely predictable. If I apply, anybody can do it. There's no key in a hash function. It's completely deterministic. The same message is always transformed into the same output, which is called a digest. For example, a digest has a small number of bits, like shown here. So it maps a longer message to a small one, but it appears to be random in the sense that if I have a given digest here, it's very hard, or in practice impossible, to forge a message that will produce exactly this digest here. So it is like a message authentication code, but it is not a message authentication code because there's no key here. Anybody can do that. But we use this when we want to apply, for example, RSA, because RSA requires the only thing that RSA can sign is one block here. We could sign each of the blocks separately, but that would be heavy. So what is done typically is you hash a long message or an entire text or an entire software. When you download software for Linux, for example, if you download for Apple or Windows, then you upload it from the website or for the shop, for the store of Microsoft or Apple. So the authentication problem is solved by relying on Microsoft or Apple. But for Linux, you don't know. So you will typically also you will hash and sign the software. And so the message can be 1 gigabyte of program, for example. That is translated into one digest, to which you apply RSA to obtain the signature. We've seen one hash function here. This could be used as a hash function. We know it's not very secure, but the hash function doesn't need to be secret. The keys could be secret. So that is an example of a hash function that translates a large number into a very small number. Well, this one is not very good. It's not very good because it has a lot of linear structure that make it easy to attack. For example, if you remember this first example here, if I apply this to this text, I obtain the hash F7. If I change the destination, and I will sign the hash, of course, later with using RSA. If I change the IBAN destination number, I obtain a different hash value, a different digest here. So that breaks here. That's a naive attacker that has changed this. It will be detected. But the most subtle attacker will do this. Here, what I've done, I've inserted empty space character, and I've computed how many space characters I need to add into the text such that the hash is F7. And it's possible. So I just add a number of spaces here. So if I'm lucky, if this is done manually, the receiver will read the text and say, oh, there are spaces, but okay, why not? And the hash is correct here. So the hash is the same as the hash that was sent separately on another channel to validate another message. So that's an example of a bad hash function. I was able to do what I call forge a collision. I knew this is the message I want to attack. I know its hash value that will be sent. I am the attacker in the middle doing ARP forgery. I obtain this message. I know that the recipient will compute the hash and apply the signature to the hash. So one way for the attacker is to make sure that the forged message has the same hash as the original message. And here it's possible. It is possible to create a message on which I have enough degrees of freedom. If it's a text message, there's usually a lot of freedom by using empty space, carriage return, new line, things like this, all of which are interpreted as characters that will be used by the hash, will modify the hash. If the hash is such that I can compute, solve the problem of where to insert my white spaces such that the resulting hash is what I want, then that's a bad hash. It's a hash system that can create, on which it's possible to create what we call a collision. People call it a collision because the F7 is the same for this message and for the original message here. So we have two messages that have the same hash. Collisions are impossible to avoid by the pigeonholes principle. What is the pigeonholes principle? Well, it says that if you have 10 million pigeons to put into 200 holes, there will be at least one hole in which there are at least two pigeons. If there are more pigeons than holes, there must be a collision. There must be at least one hole where there are two pigeons here. In mathematical terms, if you have a mapping from a set that has a larger cardinality than the destination set, the mapping cannot be injective. There must be two objects that have the same image. It's the same here. I have a hash, which is 256-bit, that I apply to messages that live in a space of millions of bits, perhaps. So there will be messages that will have the same hash automatically. If I wait long enough until the end of the universe, if I look at all the astronomical number of messages that are creating, there will be collisions. So collisions cannot be prevented, unlike when we do cryptography. When I encrypt a message, two different messages are encrypted to two different plain texts, but with hashes, of course, not so that. But I should make sure that it is very hard, other than by brute force, to forge a collision. Forging a collision means computing a message that serves my purpose, that could be interpreted by the destination as a valid message to induce the destination to doing something that I want them to do, while guaranteeing that the hash will be, presumably, what the hash was sent on the legitimate message. So forging a collision should be extremely difficult. And that's a hard thing to do. And like for AES, there are mechanisms, hash systems, that are known to be collision resistant. So today it's SHA-2 and SHA-3. Those are two systems that are known to be, or considered to be, collision resistant. Not so long ago, there were MD5 and SHA-0 that were used a lot. And then somebody, like in Homer's cipher, Homer's hash system, found a way to analyze, in fact, by the same mechanism I've shown, by inserting empty spaces into PDFs, was able to change the PDF such that the signature of the PDF was exactly whatever we wanted it to be, which was the signature of the original document that I have modified. So, like for AES, hash functions, we call them cryptographic hash functions. So it doesn't mean there is a key, but those are hash functions that are good enough to be used for a signature, that can be in which a collision is very hard to engineer. So cryptographic hash functions have existed in the past. In fact, MD5 is still used by some systems, so such systems can be attacked. And same as for AES, today we use SHA-2 and SHA-3. Perhaps in 10 years from now, somebody will find a clever attack on SHA-2, and any system that uses SHA-2 should not use it anymore. So a hash function can be used to make a long text shorter, and then we can apply an RSA signature, as we explained before. But we can use it also as a replacement to AES MAC by, we can create a message authentication code, in which case it's called HMAC, by taking a key, a secret key, and merging the secret key with the message in simplest way. So this double line means the concatenation. So I add to the message the secret key, I hash it, and then I hash the key plus the message, and that is what is called a tag here. So this is 256 bits, not more. So that's an alternative to AES, to CBC MAC using AES that can also be used here. And this is what is used for what is called two-factor authentication with authenticators. Probably some of you have used it already. You can use Google Authenticator or Microsoft Authenticator. I'm sure there are others. That solves the problem of passwords attacks. So many systems will require when you log onto the system, for example, when a teacher enters the grade into the academic system, we need to sign to do double authentication. So if our password is stolen, then we also need not just to steal the password, but to steal also the secret key that is in the authenticator. So what is the authenticator? Well, you download the app called Google Authenticator. Then you log into your Google account. You must have a Google account or a Microsoft account. If you have a Microsoft account or Apple, you certainly have an account to one of those GAFAs. And then once you log into the system here, your application, the app that you have downloaded will share with Google a secret key, which is a long sequence of bits that is secret, and then you trust Google that Google keeps it secret. But since the goal is to authenticate you with Google, everything depends on the security of Google here. And then whenever you log to the EPFL website, for example, the app that you have, your Authenticator app, will compute an HMAC, like I've shown before, which is a hash of the message that you're sending and the current time rounded to the next 30 seconds, for example. So we take the current time rounded to next 30 seconds, we hash it with a secret key that gives you a number. And this number is also known to Google Authenticator, because to the website of Google, because they have the same secret key, and hopefully the time is also the same. So when you log into the system, you give not your secret key, of course. Giving the secret key of the internet would be stupid. So you give the result of this, which is the HMAC. The same HMAC can be computed by Google Authenticator, and then that proves that whoever is at the other end knows the secret key, therefore is you. Incidentally, we find here a dependency on time synchronization, which is another effect of security. Today's security requires all systems to be time synchronized for this, for example, but also for other reasons, like a secret key or a private key or a public-private key pair might be repudiated. For example, if you did RSA 20 years ago, we were using keys that were a few hundred bytes. Today, they should not be used anymore. But how does my computer know that this is no longer valid? Well, because there is a date at which this system has expired and was not renewed. So an attack on a system can consist in changing the clock such that this computer believes it is living in 1995. So it will use crypto systems that were valid in 1995, which of course are attacked, connect to a website, which is an impersonated website, and this is one of the possible attacks. So that's another reason why we need a time base. Of course, you've seen the PMU system. PMU systems require a very accurate time base, GPS type of accuracy. This does not require that type of accuracy. It requires the same accuracy as our watch, up to a few seconds or minutes even. But that's a side effect here. Without time, the systems today do not work well. Voila, yet another little quiz. It's a good idea if you have a phasor measurement unit infrastructure or a smart grid in general to authenticate and perhaps also encrypt everything. So one simple way is to encrypt at the PMU side by sending to authenticate the PMU messages sent to the PDC. That will make impossible an attack that would consist in forging the PMU messages. But which key should we use? I close the poll in a few seconds. Closing. Majority says A, which is the correct answer. If we use anything else, if we use the private key of the PMU, then the PDC can decrypt it with the public key. No, PMU, sorry, the PDC. If we use the private key, the PC can decrypt it, but it doesn't, sorry, PMU sends messages for verification. PDC uses PMU's public key, exactly. So the PDC cannot use the PMU's private key because it's private and is not stored in the PDC. And the other two will not prove anything to the PDC. Those are the PDC's private keys, what would be used if the PMU had encrypted the message to make it secret, which we probably need to do in addition, but would not serve this purpose here. One last quiz, a bit more complicated. So this letters here is what you read when you read the doc of your socket, secure socket software, for example. CBC AES, that's what we've seen, the tag that we saw an hour ago, uses symmetric cryptography of AES chained to produce a tag. HMAC SHA-512 means this is also a tag using a hash function and a key using the mechanism we've seen. Essentially, you combine the message and the secret key, and then you hash that, and that gives you also another way of doing a tag. And SHA-256 is simply hashing. There's no key. Here you apply the hash to the message here. Wow. I close in a few seconds. I don't close because I'm not happy with the answers. So. Try again. Talk to your neighbor and see who convinces whom. So try again if you change your mind. Good, I'm closing, last attempt. There's a tie between A and H. No, H is the majority. So the pedagogical theory that says if you talk to your neighbor, the truth is imposing itself by as the only best solution. I'm not sure this is always true because you also have engineers of misinformation, but that's another story. None of them works. I mean, you have 10,000 bits, and the pigeonhole principle says whatever you do doesn't matter. If you reduce it to 256 bits, there can be collisions. So you cannot be sure that this It's true. But the hope of all those three systems, the three of them today are considered to be secure. So that means it's very, very hard for an attacker that has the M prime, for example, the attacker wants to create an M prime, it's very, very hard to have a C prime that would be equal to C, the one it wants. But collisions are possible by chance. Voilà, we do a break, another break, and after the break, we will talk about secure transport.